Let's take a look at today's lesson. So today is, it's like 6.1a. I guess I didn't put an A in here. let's just add it. Okay, it's 6.1a. This is on linear angular speed and degree. DMS is just shortened notation for degrees, minutes, seconds. So those are the topics that we're going to be talking about today. All right, so let's kind of start with formulas. Okay, we've talked about formulas, how it's important for us to, remember formulas. So what you might want to do, is you might want to highlight. So linear speed is basically this. This is just full. It's arc length, which is, we remember from last time, the formula for arc length, which is S. If you recall, remember the formula S equals R theta. Okay, so see where the S just moves to R theta. So linear speed, the formula for linear speed, one of the formulas is simply, it's arc length over time, or distance over time. Okay, so that's an important formula for us. So this was arc length. Okay, this was arc length. And this is linear speed. Now I'm going to talk about the difference between linear and angular speed in just a moment. I just want to go over the formulas first. So angular speed has a formula itself. This is the Greek letter omega. And usually they use that Greek letter to designate angular speed. I mean, you don't need to memorize that, but that's usually what they do. And angular speed is theta over time. Okay, theta over time. So let's compare and contrast. Well, one more thing. We can relate those, we can see those together, that linear speed is actually simply the radius times the angular speed. That's what it is. And this angle, let's just make a note, this theta, just like last time, has to be in radians. Okay, that theta measure must be in radians. If it's not, you just need to convert it. So there's a relationship between these. So here, let's talk about linear speed. Okay, so I'm going to put this in terms of a piece of playground equipment. Okay, this is the easiest way I can think about it. Maybe when you were younger, or maybe now, I don't know. There's a piece of playground, it's like a circle, and it has like rails on it, and you get on it and it twirls around. You know what I'm talking about? I don't really know what it's called, but you know what I'm talking about, right? You can stand in the center of it. There's like, it's empty in the center, and then you can stand to the edge of it. Have you done that? Because you know what I'm talking about, right? So linear speed has to do with the radius. So if you stood on that piece of playground equipment in the middle, did you feel like you were moving very fast? You don't, do you, right? You're just turning around in a circle. You're not really, you don't feel the force of the movement. But the farther out that you move on that circle, have you ever been on the edge of it, holding on by the, on the edge? You should feel a really tremendous pull. That's because you are physically moving faster. Your linear speed is faster. That's why you feel the pull, right? And versus being in the middle. So that's linear speed. It depends on the radius. The farther away you are from the center, the faster you're going to go, because you are going over more distance. Right? The farther away you are, the larger the radius is, the more distance you are traveling in the same amount of time. Does that make sense? So that's linear speed. Let's compare and contrast it with angular speed. Angular speed doesn't rely on the radius at all. So in that same example of playground equipment, if you are standing in the middle of it and it rotates one time around, how many angles have you passed through? One time around would be 2 pi, right? If you're standing on the edge of it and it moves one time around, how many angles have you rotated through? 2 pi. It doesn't matter where you are on the object, you're still going to accumulate the same amount of angle measure. Does that make sense? So that's the difference between them. That is the only difference, is the radius. In linear speed, the radius has a huge impact on how fast you're going to go. But in angular speed, it makes no difference what the radius is. It's simply adding up the number of, the number of angle measures you've gone through. Okay, so that's the difference. So we're going to actually, get into this. Let's just talk about these 3 important facts. Okay. These are important when you're going to do word problems. So these apply to word problems. Okay, you will experience these in some word problems that we're going to do. So we're still in the theoretical field, right? I'm still explaining to you what this is, how it works, how they relate to each other. So let's think about if we have 2 rotating objects that are connected by their rims. Let me give you an example. Let's say, you have a bicycle, right? And so here's the wheels on the bicycle. And and I'm not a very good artist. There's the chain that typically goes around like that. There's like a cog right here. Maybe I have a picture on the other page. Oh yeah, here's a bicycle. This is much better. Okay. So there's like a chain, right, that goes it wraps around here, and it wraps around like where you're pedaling. Okay, and so those things, maybe there's a better one here. This is much better. Here we go. So here's where you pedal, here's where you put your feet, right? And there's a chain that connects. It's connecting this small circle to this larger circle. Okay, and probably most of us have ridden a bike, right, at one time or another in our lives. You remember the chain on the bike? So I'm talking about that chain that connects those 2 circles together. And as you pedal, the gears affect the other circle, right? It causes you to move, right? It makes you move. So since those 2 circles are connected together, see how they're connected together? They're rotating together. So since that is true, since the 2 rotating objects are connected by their rims, then their rims have the same linear velocity. Okay, the same. Because kind of imagine if they didn't. If one of the objects was rotating faster than the other, it would like break all apart, right? You wouldn't go anywhere. It would be bad. Right, so if 2 rotating objects are connected by their rims and they have the same linear velocity, okay, this is significant. It's linear, okay? And I want you to think about angular velocity. Do you think they would have, if they're different sizes? So in that example, the one on the wheel was really small. Do you think those 2 circles have the same angular velocity? No, because if that little one turns only as many times as the front one, aren't we going to have a problem? Right? Because the angular velocity doesn't really matter. So that doesn't matter about, the radius, angular velocity. Well, I guess we have an exciting flash flood warning or something. Okay. We can't really do anything about it in class, right? I don't know. Okay, so that's just I'm just trying to walk you through this because these are the concepts that are going to come to you on these problems. You're going to have to kind of think through these concepts. Okay, so that's if they're connected by their rims. If they're connected by their rims, they will have the same linear velocity, but not necessarily same angular. Okay, why do I say not necessarily? Couldn't they be the exact same size of circle? Couldn't they? Yes, exact same size of circle. Okay, they could be. All right, so I hope that's not on the video, but it might be. I don't know. That's all right, just for us, right? Just for us. Okay. So number 2, all points on the same rotating object have the same angular velocity. Okay, so that goes back to the example I gave you about that piece of playground equipment, right? That piece of playground, it doesn't matter where you're standing on that circle, you're going to rotate around the same number of times, right? You're going to accumulate the same number of angle measures. If you rotate 2 times around, then that would be 4 pi, right? Because 1 time around a circle would be 2 pi. 2 times around a circle would be 4 pi. You with me? Same angular speed. It doesn't matter. If you're all points on the same rotating object have the same angular velocity, will they have the same linear velocity? Will they? If I'm standing in the center and my radius is 0, and I move to the outside and my radius is 2 feet, am I going to have the same linear velocity? No. No. So this, we'll just write here, just a little note to ourselves, not true for linear velocity. Because linear velocity relies on the radius. It changes depending on the length of the radius. Okay, the last kind of little concept that we need to talk about. Let's talk about if 2 rotating objects are connected so that they rotate as a single object. Okay, let me give an example. Let's say most of you are driving a car, or you've been in a car sometime in your life, right? You know, they have, so there's a tire and there's a wheel, right? Like the wheel thing. Now, I'm not talking about the fancy new kind of wheels that turn differently. I'm just talking about regular old wheels and tires. So this wheel, you know, they usually have whatever. Okay, it is not the size of the tire, right? The tire is bigger than the wheel. I mean in radius, right? It's a larger radius. But they move together as one. Right? They move together as one. These 2 rotating objects, even though they have a different radius, they're different sizes, they're connected and they rotate as a single object. They would have the same angular velocity. Okay, they would have the same angular velocity. Okay. Would they have the same linear velocity? Would they? Do they have the same radius? No, no. So they won't have the same linear velocity, but they will have the same angular velocity. So not same linear. I hope in all of this that you really kind of get into your mind that linear velocity is all about the radius. It's all about the distance that you're traveling. It is, you know, it's all about that. And angular velocity has nothing to do with the radius. Okay? So now let's move to the other topic that we're going to talk about today, which is degrees, minutes, seconds. Last time we kind of investigated minutes. We did degrees and minutes. If you recall, we added those 2 angles together. Remember that? And you know, we converted. So this idea is really old. It dates back to the Babylonians, and they used degrees, minutes, seconds to navigate, like when they were on the ocean, you know, when they were traveling. So we still use degrees, minutes, seconds with navigation kind of stuff, like the globe, you know, if you look at the latitude and all that, that's typically degrees, minutes, seconds. So what we're going to do is we're going to take a number and we're going to convert it to degrees, minutes, seconds. Now, your calculator, I'm pretty sure there's a button that will do this. I don't remember where the button is, but I want you to know how to do it if you just have just a plain old calculator. Just a plain old calculator. So here's what we're going to do. This is called a decimal degree. That's a decimal degree. We're going to turn that measurement from a decimal to degree to DMS, degrees, minutes, and seconds. So the degree part is good. So we're just going to start, so 35 degrees. The whole number, The whole number, you don't do anything to the whole number. It's just the degrees. It's the fractional part that we have to mess with. So let's go over here to the side. Let's take 0.72 and we're going to multiply it by 60 because, let's talk about why. This is a part of a degree, right? It's not a full degree. It's 0.72 of a degree. And we know that there are 60 minutes in 1 degree. So I'm multiplying 60 times 0.72 to see how many minutes I have. So when I do that, I get 40, I'm just using a calculator to do this, 43.2. The whole number, that's how many minutes there are. Okay, that's how many minutes. So let's go back to our answer. So 35 degrees, 43 minutes. Now we have this fractional piece, 0.2, that's 0.2 of a minute. It's part of a minute, right? It's not a whole minute. So we're going to take that fractional part of a minute and we're going to turn it into seconds. So we're going to take the 0.2 and we're going to multiply it by 60 because there are 60 seconds in a minute. And that will give us, it turns out to 12, a whole number. So then I'm finished with 12. Now, sometimes the minutes don't turn out into a whole number. Typically, it just depends on how precise that, they're going to be. I would recommend just rounding it to a whole number, but we'll see what your homework does. I don't know how, your homework will be specific, and you have some homework problems on converting to degrees, minutes, seconds. Okay? So how are we? Now let's see, what if we wanted to check this out? What if we wanted to see if we were correct? What would we do? We would do 35 plus 43 over 60 plus 12 over 60 times 60. It's not 60 times, or what is 60 times 60? It's 3,600, right? So you might not have thought about that before, but there are 60 minutes in an hour, and there are 60 seconds in a minute. So how many minutes in an hour? 3,600, right? Does that make sense where the 3,600 came from? If we do that, and just for fun, I'm just going to pull my calculator up. Let's just add that together, and we should get back to 35.72 if we've done it correctly. So let's do 35 plus, let's see, we had 43 over 60, and then plus, and then we had 12 over 3,600, and then control enter, and that gives me back to 35.72. Okay, so you can go back and forth between degrees, minutes, seconds, and decimal degrees. Is that okay? Is everybody okay? Okay. All right. So we have a couple of word problems on the second page to work through. I think there's 3. So let's do that. All right, so this is where we have word problems on linear and angular velocity. Okay, so yay, I know we love word problems, right? You're like, oh, joy, second day back, we get word problems. Okay, we got this. So we have a Ferris wheel. Y'all know what that is, right? The big circle with the, Ferris wheel, okay. It rotates 3 times each minute. 3 times each minute. They're giving us some information, so let's just kind of highlight that. Or, that's going to be important. So it rotates 3 times each minute. We're going to have to figure out what that is in just a moment. The passengers sit in seats that are 25 feet from the center of the wheel. Okay, so let's kind of get a picture of this. So we've got the wheel. We've got, here's our little seat right here. Okay, I'm a terrible artist, sorry. That doesn't look like a seat. Let's put like a little awning on it. Okay, so that's 25 feet. Okay, I know that's a terrible seat, sorry, but you're with me, right? That's where they're sitting. They're 25 feet from the center. All right, so let's look at what they want. First, they want what is the angular velocity of the wheel in degrees per minute and radians per minute. So now they're going a little crazy on us. So angular velocity. When they ask you for something, the first thing that you should do is write down the formula. If you don't write down the formula, you're going to be lost. You don't know what to do. What do you mean? Right? Write down the formula. It gives you direction. So linear angular velocity is omega equals theta over t, or angle measures divided by time. All right, so let's think about that for a second. Now they talk to us, and I highlighted in green, they talk to us about rotations 3 times each minute. Okay, let's think about that for a second. So this wheel rotates, so let's say you're at the top of it. It's going to go around, 1 time, 2 times, 3 times. Okay, 3 times. So how many angle measures, so we want the angle measures and we want it to be in radians. How many angle measures would that have accumulated? What is 1 time around? 2 pi. 6 pi. So 3 times around would be 6 pi. So we know that omega is going to be 6 pi. And what is the time that they gave us? They told us that it does that in a minute. So it's 6 pi per 1 minute. That is our angular velocity. And that is in radians per minute. So that's our first, well, that's radians per minute. That's this one. Now they want us to convert to degrees per minute. Well, we know how to do that, right? We've converted from radians to degrees. That's not a big thing. So another way that we could write it would be, so it'd be 6 pi times, let's just do, I'll erase my fun example. Let's just do 6 pi times, what's my conversion for radians to degrees? Yep, or 180 over pi, right? Because we want to get rid of the pi. Right, we want to get rid of the pi. So it would be 6 times 180, and you would typically have a calculator for this. So you just multiply that out, and you actually get 1,080 degrees per minute. So we found the angular velocity. Is angular velocity going to be important to us when we start looking at linear velocity? Yes. Isn't linear velocity just angular velocity times r? Yes, that's going to be important, right? They want the linear velocity of the passengers in the seats. Well, okay, we have angular velocity of the passengers in the seats. Let's go for linear. And what do we need for linear? We need the radius. So our formula, the one that connects angular and linear, is linear velocity is angular velocity times the radius, omega times r. And these formulas you need to know. Okay, you need to know them, and we're not going to give them out. So add that to, we talked last time about maybe making flashcards or doing something. Maybe you could do a Quizlet, I don't know. It's just add it to your list to know. Okay, there's just a few per, unit or so. Okay, linear velocity. So we do, now they want miles per hour. Okay, let's not worry about the units for just now. Let's just get the linear velocity. So linear velocity is, so we've got linear velocity is going to be omega, which was 6 pi per minute, times the radius, which is 25 feet. Okay, can we all agree that that is good? My only problem now is units, and so we get to do something called dimensional analysis. Yay! You probably did that, I don't know, in science classes at some point, and maybe you're like terrified and you're like, oh my gosh, not dimensional analysis. When we write the units by it, it's not going to be too bad. Guys, we just need to get the proper unit. If I want to switch from minutes to hours, see how the minutes is on the bottom? I need to multiply by minutes on the top. So 60 minutes and 1 hour. Okay, time, great. Got the time taken care of. Yay. Okay, got the time taken care of. Now we want miles and we have feet. Okay, so you would, and we'll probably give you conversions. I don't need you to memorize 5280. 5,280 feet are in 1 mile. Now you really should know 60 minutes or an hour, right? I mean, we know that. But I don't want feet, so I want feet to be on the bottom. I want 1 mile to be on the top. And it's 5,280 feet in 1 mile. So I put all this in my calculator. Seriously, I just put all those numbers. So I put a 6 pi times, do I need to go over the calculator or are we okay? Do I need to put it in the calculator? We're okay, right? We just put all that in the calculator. And so this is going to give me, now we're in a Ferris wheel. What do you think if this said 20 miles per hour, that would be okay? Have you ever been in a Ferris wheel that was moving 20 miles? And 20 miles doesn't seem that fast, but I promise you that is really fast. Or 50 miles an hour. If our answer is 50 miles an hour, we need to be worried, right? We did something wrong, something's wrong, because they're not going to make a Ferris wheel that goes 50 miles an hour. Okay, so just we need to pay attention to the number. So the velocity would be I just put it in the calculator, 3549 miles per hour. And you should go to the thousandth or 10 thousandths is fine, but at least the thousandth, which is 3 decimal places. Okay, yay. Are we doing okay? You're like, sure, Dr. Wright, we're doing great. Okay, number 2. The pedals on a bicycle turn the front sprocket, and that's where this picture comes in. Okay, turn the front sprocket at 8 radians per second. Okay, so let's kind of label this. So 8 radians per second. Is that angular or linear? What is that? We can tell by the units. Do you see any distance units on that? Just an angle and a time. You can tell by the units. If that doesn't make sense to you, you should write that down. You can tell by the units what they're giving you. That's radians per second. So that's angular. So this has 8, and I'm just going to write radians per second. That's omega for the front sprocket. Okay. The front sprocket. Okay, the sprocket has a diameter of 20 centimeters. Okay, so this is 20 centimeters. The back sprocket has a diameter, it's diameter, not radius. Ooh, about got us, right? Or about got, I need to go all the way across. This is diameter. Diameter is 20, and this diameter is 6. Okay, so that's the information that they gave us. Great. Find the linear velocity of the chain. Let's write down our formula. V equals omega r. Okay. Do we have omega r? Do we have the linear velocity of the chain? Do we have an angular velocity that was given to us? We've got 8, what is it? Let me go back, sorry. 8 radians per second. Okay. 8 radians per second. And so our linear velocity is going to be 8 radians per second, and we don't include a pi. They didn't include a pi. It's just 8 radians. Right, don't put a pi in there. 8 radians per second, and we know its radius is, and we want the chain. Okay, so since we use the angular velocity of the front sprocket, we have to use the radius of the front sprocket. You cannot mix and match like that. You've got to use this, so that has to be 10 centimeters. So our linear velocity is 80 centimeters per second. Okay, not too bad. Oh, now they're getting crazy on us. Find the angular velocity of the back sprocket. Okay. Do the back sprocket and the front sprocket have the same linear velocity? Look at this little thing up here. Two rotating objects connected by their rims have the same linear, two rotating objects that are connected by their rims have the same linear velocity. So they do, right? They do. That's why those little things are important. So they have the same linear velocity. So this back sprocket has, is linear, is 80 centimeters per second. And this front one is 80 centimeters per second. Are they going to necessarily have the same angular velocity? No. Okay, let's write our formula out. Angular velocity is omega equals, let's write that, since we had no linear, let's write this little guy out. Linear equals omega, or angular times r. We know linear is 80. We don't know omega, we don't know angular, that's what we're supposed to find, but we do know the radius. The radius of the back sprocket is what? 3. So we would just divide, so it would be 80 thirds radians per second. Okay. Last one. Is everybody okay? Yes, ma'am.
I might have missed you saying this, but on the first part, is there a reason why we chose the radius of 10 instead of the radius of 30?
Ah, yes, because they designated that the front sprocket moved at 8 radians per second. We have to stick with the object that they are saying that belongs to. We can't switch objects like that with angular. We were able to switch objects with linear because what? Because they rotate on the same. They rotate, they're connected by, they're connected together and rotate together. Okay. Last problem, second hand of a clock is second hand. Do we know what the second hand is? What is the second hand? Yeah, the second hand does seconds, right? You with me? Because it's the second hand, it does seconds. Okay, it's that long, it's 10.2 centimeters. So it wants linear speed of the tip of the second hand. Okay, so let's see what we have. We know the radius, we want linear, so linear equals, find the linear of the tip. Well, let's find our, we don't know what omega is, so let's write the whole formula. This is omega, but theta over t, r. This is the full thing when you don't know, we don't know. So we can't use the other formula because we don't know omega or angular, but we can calculate it. Okay, let's think about that for a second. So the radius we know is 10.2. We need to think about this. And it goes one time around in 60 seconds. Right? The second hand goes one time around in 60 seconds. Okay. Let's think about the angle measure. So if it's going one time around, how many angles does it pass through? 2 pi. So then we just put it in our calculator and we get 1.068 centimeters per second. Ooh, isn't that fun? You could go home and measure your clock. Like, oh, you could tell your parents, look, I can calculate the linear speed of the tip of this, second hand. Yay. You're like, okay, no way. It's okay. All right.